A nuclide is an atomic species characterized by the specific constitution of its nucleus, i.e., by its number of protons Z, its number of neutrons N, and its nuclear energy state. The word nuclide was proposed by Truman P. Coleman in 1947. Coleman originally suggested nuclide as referring to a species of nucleus, defined by containing a certain number of neutrons and protons. The word thus was originally intended to focus on the nucleus. Nuclides and isotopes. A set of nuclides with equal proton number, i.e., of the same chemical element but different neutron numbers, are called isotopes of the element. Particular nuclides are still often loosely called isotopes, but the term nuclide is the correct one in general. In similar manner, a set of nuclides with equal mass number E, but different atomic number, are called isobars, and isotones are nuclides of equal neutron number, but different proton numbers. The name isotone has been derived from the name isotope to emphasize that in the first group of nuclides it is the number of neutrons that is constant, whereas in the second the number of protons. See isotope notation for an explanation of the notation used for different nuclide or isotope types. Nuclear isomers are members of a set of nuclides with equal proton number and equal mass number, but different states of excitation. An example is the two states of the single isotope 9943 Tc shown among the decay schemes. Each of these two states qualifies as a different nuclide, illustrating one way that nuclides may differ from isotopes. The most long-lived non-ground state nuclear isomer is the nuclide tantalum 180 meters, which has a half-life in excess of 1,000 trillion years. This nuclide occurs primordially, and has never been observed to decay to the ground state, or 180 W. There are about 254 nuclides in nature that have never been observed to decay. They occur among the 80 different elements that have one or more stable isotopes. See stable isotope and primordial nuclide. Unstable nuclides are radioactive and are called radionuclides. Their decay products are called radiogenic nuclides. About 254 stable and about 85 unstable nuclides exist naturally on Earth, for a total of about 339 naturally occurring nuclides on Earth. Origins of naturally occurring nuclides. Natural radionuclides may be conveniently subdivided into three types. First, those whose half-lives T1/2 are at least 2% as long as the age of the Earth. These are remnants of nuclear synthesis that occurred in stars before the formation of the solar system. For example, the isotope 238U of uranium is still fairly abundant in nature, but the shorter-lived isotope 235U is 138 times rarer. About 34 of these nuclides have been discovered. The second group of radionuclides that exists naturally consists of radiogenic nuclides such as 226 Ra, an isotope of radium, which are formed by radioactive decay. They occur in the decay chains of primordial isotopes of uranium or thorium. Some of these nuclides are very short-lived, such as isotopes of francium. There exist about 51 of these daughter nuclides that have half-lives too short to be primordial, and which exist in nature solely due to decay from longer-lived radioactive primordial nuclides. The third group consists of nuclides that are continuously being made in another fashion that is not simple spontaneous radioactive decay but instead involves a natural nuclear reaction. These occur when atoms react with natural neutrons, or are bombarded directly with cosmic rays. The latter, if non-primordial, are called cosmogenic nuclides. Other types of natural nuclear reactions produce nuclides that are said to be nucleogenic nuclides. An example of nuclides made by nuclear reactions, a cosmogenic 14C that is made by cosmic ray bombardment of other elements, and nucleogenic 239Pu which is still being created by neutron bombardment of natural 238U as a result of natural fission in uranium ores. Cosmogenic nuclides may be either stable or radioactive. If they're stable, their existence must be deduced against a background of stable nuclides. Since every known stable nuclide is present on Earth, primordially artificially produced nuclides. Beyond the 339 naturally occurring nuclides, more than 3,000 radionuclides of varying half-lives have been artificially produced and characterized. The known nuclides are shown in the chart of nuclides. A list of primordial nuclides is given sorted by element, a list of elements by stability of isotopes. A list of nuclides is also available, sorted by half-life, for the 905 nuclides with half-lives longer than 1 hour. Summary table for numbers of each class of nuclides. This is a summary table for the 905 nuclides with half-lives longer than 1 hour, given in list of nuclides. Note that numbers are not exact, and may change slightly in the future. If some stable nuclides are observed to be radioactive with very long half-lives. Nuclear properties and stability. Atomic nuclei consist of protons and neutrons bound together by the residual strong force. Because protons are positively charged, they repel each other. Neutrons, which are electrically neutral, stabilize the nucleus in two ways. Their copresence pushes protons slightly apart, reducing the electrostatic repulsion between the protons, and they exert the attractive nuclear force on each other and on protons. For this reason, one or more neutrons are necessary for two or more protons to be bound into a nucleus. As the number of protons increases, so does the ratio of neutrons to protons necessary to ensure a stable nucleus. For example, although the neutron-proton ratio are 3:2 is 1:2, the neutron-proton ratio of 23892 U is greater than 3:2. A number of lighter elements have stable nuclides with the ratio 1:1. The nuclide 4020 California is the observationally the heaviest stable nuclide with the same number of neutrons and protons. All stable nuclides heavier than calcium-40 contain more neutrons than protons. Even and odd nucleon numbers. The proton-neutron ratio is not the only factor affecting nuclear stability. It depends also on evenness or oddness of its atomic number Z, neutron number and consequently, of their sum, the mass number A. Oddness of both Z and N tends to lower the nuclear binding energy, making odd nuclei, generally, less stable. This remarkable difference of nuclear binding energy between neighboring nuclei, especially of odd A isobars, has important consequences. Unstable isotopes with a non-optimal number of neutrons or protons decay by beta decay, electron capture or other exotic means, such as spontaneous fission and cluster decay. The majority of stable nuclides are even proton, even neutron, where all numbers Z, N, and A are even. The odd A stable nuclides are divided into odd proton, even neutron, and even proton, odd neutron nuclides. Odd proton, odd neutron nuclides are the least common.